Finding the kth-smallest element in union of sorted arrays. I was studying the article on finding the kth-smallest element in the union of two sorted arrays at LeetCode. I don't think that the algorithm is correct. There is this line: we make an observation that when I is lower than bj, then it must be true that I is lower than bj1. On the other hand, if bj is lower than I, then bj is lower than I1. How can it be true for any I and j? And secondly, this line also baffles me. We try to approach this tricky problem by comparing middle elements of a and b, which we identify as I and bj. If I is between bj and bj1, we have just found the I plus j plus 1 smallest element, although it comes out to be true. Can anyone explain the reason? I really want to understand the algo. I have done it by merging the arrays, but that takes O(n) time, compared to O log n time here.
We make an observation that when I less than bj, then it must be true that I less than bj1. On the other hand, if bj less than I, then bj less than I1. How can it be true for any I and j? It isn't true for all pairs of I and j. The article considers a special situation. First, it is assumed that there are no duplicates, not even in the form of common elements of A and B. Second, the conclusion that is made under the condition that neither of holds. So by excluding these configurations, I is lower than bj equals I is lower than or equal to bj1 and bj is lower than I equals bj is lower than or equal to I1 follow immediately, and the strict inequalities then follow by the assumption that no duplicates exist. We try to approach this tricky problem by comparing middle elements of A and B, which we identify as I and bj. If I is between bj and bj1, we have just found the I plus j plus 1 smallest element. In array B, there are j elements smaller than bj, and in array A, there are I elements smaller than I. Indices start at 0. So if bj1 is lower than I is lower than bj, both arrays together contain exactly j plus I elements that are smaller than I. What changes if there are duplicates? Not much. We still consider the situation where I plus j equals k1. Let us assume that I is lower than or equal to bj. What if I equals bj? What if I is lower than bj? In case 1, let m be the smallest index such that m equals I, and n the smallest index such that bn equals bj. Then in both arrays together, there are exactly m plus n is lower than or equal to I plus j equals k1 elements strictly smaller than I, and at least I plus 1 plus j plus 1 equals k plus 1 elements not larger than I. Hence the kth-smallest element is equal to I. For 2 we have 3 cases to consider. A. bj1 is lower than I. B. bj1 equals I. C. bj1 is greater than I. In case A, we have j elements in B that are not larger than I, and they are all strictly smaller, and we have m is lower than or equal to I elements in A that are strictly smaller than I, m is above, and an unknown number, but at least I m plus 1 elements equal to I. So there are exactly j plus m is lower than or equal to j plus I equals k1 elements in both arrays together that are strictly smaller than I, and at least j plus m plus I m plus 1 equals j plus I plus 1 equals k elements not larger than I. Hence the kth-smallest element of both arrays together is equal to I. In case B, the same reasoning shows that the kth-smallest element of both arrays together is equal to I. In the remaining case, I is lower than bj1, things become hardly more complicated. Array B contains at least j elements not larger than bj1, and array A contains at least I plus 1 elements strictly smaller than bj1, hence the kth-smallest element of both arrays together is at most as large as bj1. But it cannot be smaller than I. B contains at most j1 elements smaller than I, so both arrays together contain at most I plus j1 equals k2 elements smaller than I. So we can still discard the part below I from the array A and the part above bj1 from the array B and proceed as without duplicates. All that changed was that a few strict inequalities had to be replaced with weak inequalities. The code would be more efficient if starting indices and lengths were passed instead of slicing, but slicing yields shorter code.
You are interpreting these statements in isolation, but they build on one another. Here's the text that, I think, you're referring to. Maintaining the invariant I plus j equals k, 1, if bj1 less than I less than bj, then I must be the kth-smallest, or else if I1 less than bj less than I, then bj must be the kth-smallest. If one of the above conditions are satisfied, we are done. If not, we will use I and j as the pivot index to subdivide the arrays. But how? Which portion should we discard? How about I and bj itself? We make an observation that when I less than bj, then it must be true that I less than bj1. On the other hand, if bj less than I, then bj less than I1. Why? Breaking this down into subpropositions yields the following interpretation, keeping in mind that indexing starts from 0, but that A0 is the first smallest item, and A1 is the second smallest item, and so on. I plus j equals k, 1, invariant, by definition. Posit that, bj1 is lower than I is lower than bj. Then I must be the kth-smallest. This is because I is greater than I items in A and is greater than j items in B. So it's greater than a total of, I plus j equals k, 1, items. That means its index in a merged A vertical bar B list would be, k, 1, and so it would be the kth item in that list. Posit that, I1 is lower than bj is lower than I. Then bj must be the kth-smallest, by the same line of reasoning in 2. Now posit that both, a, bj1 is lower than I is lower than bj, and, b, I1 is lower than bj is lower than I, are false. Then it follows quite obviously that if, I is lower than bj, then, a1 is lower than bj1, because otherwise, a, would be true. And likewise, if, bj is lower than I, then, bj is lower than I1, because otherwise, b, would be true. I'm taking you at your word that you want an explanation of these statements rather than of the algorithm as a whole. But I'll say more if you like. Note also that, as Daniel Fisher's answer reminds me, the above reasoning only holds if there are no duplicates. Call that proposition 0.